What's something people don't know about star collisions? It's a question that conjures images of pure, unadulterated destruction, and while that's part of the story, it's far from the whole truth. These events are not just endings, they are spectacular, universe-altering beginnings. They're cosmic alchemy, turning simple atoms into the universe's most precious and complex elements. They also sing, emitting ripples called gravitational waves across the very fabric of space and time, a cosmic symphony we are only now learning to hear. These collisions are the most violent shows in space, but they are also the architects of the cosmos as we know it. To understand this cosmic drama, picture two stars locked in a tight, shrinking orbit. They might be ordinary stars like our sun, or the hyperdense remnants of stars long dead. For most of their lives, they exist in a stable binary system, a celestial partnership that can last for billions of years. But nothing in the universe is truly static. As these stars orbit each other, they constantly stir the fabric of space-time, radiating away energy in the form of gravitational waves. This is a prediction of Einstein's theory of general relativity, a constant, subtle loss of orbital energy. For millions, even billions of years, this whisper of gravity slowly pulls them inward. The process is imperceptibly slow at first, but as they get closer, the energy loss accelerates. The whisper becomes a hum, then a roar. Their orbital dance quickens, spiraling faster and faster in the final moments, until one day, in the final frantic milliseconds, they slam together in a violent collision. The nature of this cataclysm depends entirely on what kind of stars are colliding. If they're normal, main-sequence stars like our sun, expect violent stellar outcomes. The collision tears them apart, merging their hydrogen and helium cores into a single, much larger and highly unstable star. This triggers a massive explosion, a specific type of event called a luminous red nova, releasing enormous energy across the system. Powerful shockwaves blast outward, reshaping surrounding gas and dust, potentially even triggering the birth of new stars and planets. And what's left is often a messy merger of stellar cores and debris, a new rapidly spinning star called a blue straggler, appearing younger and hotter than its neighbors. Now, what if the colliding bodies are white dwarfs, the dense, burnt-out cores of sun-like stars? If their combined mass pushes past a critical threshold known as the Chandrasekhar limit, the result is a cataclysm of a different order, a Type Ia supernova. This isn't a merger, it's total annihilation. The entire structure detonates in a thermonuclear explosion so consistently bright that astronomers use them as standard candles to measure the expansion of the universe itself. But if at least one of the colliding objects is a neutron star, the city-sized, ultra-dense corpse of a massive star, things escalate into a realm of physics that defies imagination. As two neutron stars spiral together, their immense gravity, trillions of times stronger than Earth's, wages a tidal war. In the final moments, this intense gravity tears hundreds of millions of tons of neutron-rich matter off the star's crusts and slings it outward into space. When the cores finally collide and merge, they create a kilonova, a luminous explosion, but one fundamentally different from a normal supernova. A kilonova is about 1,000 times brighter than a classical nova, but typically only 1/10 to 1/100th the brightness of a supernova. Its light curve is also distinct, peaking and fading much faster, over a matter of days rather than weeks or months. The color of the light evolves too. Initially, the fast-moving ejecta along the poles glows blue, but the slower, denser material flung out along the orbital plane glows a deeper red. That glow can outshine its entire host galaxy for many days, and it's within this chaotic, expanding cloud of debris that the universe performs its most profound alchemy. The extreme conditions trigger a chain of nuclear reactions called the rapid neutron capture process, or R process. Neutrons are captured by atomic nuclei faster than the nuclei can decay, building simple elements into heavier ones in a cosmic flash. This is how they forge heavy elements like gold deep in the ejecta. Platinum, uranium, and other rare heavy elements are all synthesized in the unimaginable heat and pressure of this blast. The gold in your jewelry, the platinum in a catalytic converter, the uranium in a nuclear reactor. The vast majority of these elements on Earth were born in the heart of a kilonova billions of years ago and scattered across the galaxy. The aftermath of these collisions can also birth new black holes from the merged cores. If the combined mass of two neutron stars is great enough, the remnant will collapse under its own gravity almost instantly, forming a new black hole. Or in an even more extreme scenario, a neutron star might collide with an existing black hole, a final fatal plunge into oblivion. And in the most energetic of these events, they can launch short gamma-ray bursts, brief, mind-bogglingly powerful jets of energy. As the newly formed black hole or hypermassive neutron star spins rapidly, its powerful magnetic fields can channel in falling matter into two opposing beams. These jets, containing more energy than our sun will produce in its entire lifetime, blaze across the cosmos at near light speed, lasting for less than 2 seconds. If one of these beams happens to be pointed directly at Earth, we see it as a short gamma-ray burst, one of the most luminous events in the known universe. And yes, throughout this entire violent process, they ripple space-time with gravitational waves we can now detect. As the two massive objects spiral closer, the frequency and amplitude of these waves increase, creating a characteristic signal known as a chirp. For the final few minutes, the waves become strong enough for our instruments to hear. Detectors like LIGO in the United States and Virgo in Italy are giant L-shaped interferometers that use lasers to measure minuscule stretching and squeezing of space-time. They can translate these ripples into audible signals, allowing us to listen to the universe's most dramatic events. On August 17, 2017, history was made. The LIGO Virgo network detected a powerful chirp, a signal designated GW170817. Just 1.7 seconds later, space-based telescopes detected a short gamma-ray burst from the same patch of sky. For the first time, we had seen and heard the same cosmic event, the collision of two neutron stars. Telescopes around the world scrambled to look, and they found it, the fading glow of a kilonova in a galaxy 130 million light-years away. The spectrum of its light confirmed the presence of freshly synthesized heavy elements, including gold and platinum. 00817 was the birth of multi-messenger astronomy, confirming decades of theories in a single, spectacular observation. These collisions tend to happen in dense stellar environments. Globular clusters, ancient, tightly packed cities of stars, are prime locations. So are the chaotic centers of galaxies where the gravitational pull of supermassive black holes can throw stars together. But don't worry, while these events are common on a cosmic scale, the odds of one happening close enough to harm Earth are infinitesimally small. The nearest known neutron star binary is hundreds of light-years away, far too distant to pose any threat. We are safe observers of this cosmic fireworks show. And our view is only going to get better. Upgrades to LIGO, Virgo, and Kagra in Japan will increase their sensitivity, allowing us to detect mergers from even farther away. Future projects like the Einstein Telescope in Europe and Cosmic Explorer in the US promise another tenfold increase in sensitivity, and the space-based LISA mission will open a new window, detecting the slow, gentle hum of supermassive black holes merging and the long, slow in-spirals of compact binaries years before they collide. Star collisions are violent, awe-inspiring, and cosmically essential. They are the universe's grand recycling program. They seeded the cosmos with the heavy elements that build rocky planets like our own. The iron in our blood was forged in the heart of an exploding star, but the gold in our vaults and the platinum in our technology were born in the even more spectacular fire of a stellar collision. These cataclysms, happening in galaxies far, far away, ultimately enabled the complex chemistry, the solid rocks, the protective atmospheres, and the very possibility of life to emerge, right here. They are a violent, beautiful reminder that in the cosmos, even the most destructive endings are the source of the most profound new beginnings.